electricity does many useful jobs. You've just seen a few examples. Now, the type of job it does is determined by the type of circuit we use to control it. Here are two strings of Christmas lights. At first glance, there appears to be little difference. But watch what happens when I remove one bulb from each string. Now, why did all of the lights go out in this one circuit and not in the other? Well, that's because we have two different types of circuits. This one is a series circuit. This one is a parallel circuit. Now, you know the laws of series circuits. It has the same current throughout the circuit, and the voltage is divided among the various bulbs. When one bulb burns out or is removed, the current path is broken and the entire circuit is disabled. Obviously, this parallel circuit is different in some way. In this lesson, we'll discover exactly what these differences are. Now, in this series circuit, it's obvious that removing any component stops all current. But it isn't so obvious in this parallel circuit, why it remains lit. The circuit on this trainer is a parallel circuit similar to the parallel string of Christmas tree lights. By using it, we should be able to figure out why the bulbs remain lit. First, notice that there's a separate path for current through each of the bulbs. Now, we refer to these paths as branches. On schematic drawings and sometimes in actual circuits, these branches are laid out as they are here. That is, the branches are parallel to one another and to the power supply. This gives us the name for this type of circuit. It's a parallel circuit. When I close this switch, I'm adding a third branch in parallel with the first two. Now observe the brilliance of these two lights as I do this again. When I close the switch, there's no effect on the brilliance here. Watch again as I open the switch. Again, no effect. But why? Well, this is because each branch is a separate path for current. We can add as many branches as we like, provided we don't overload the circuit. Keep in mind, then, that each branch is independent of all the other branches. Now, that's why the remaining bulbs remain lit when one is removed or burns out in a parallel string of Christmas tree lights. Okay, so the parallel circuit has more than one path for current. But what about the voltage? Well, notice on this trainer that each branch is connected directly across the battery. Let's investigate this further by building a parallel circuit. Now, I'll take this one out, and I'll start by connecting one bulb across the battery, like this. Now, when the bulb is placed in this manner, it's pretty obvious that the applied voltage is across the bulb. If I place a second bulb over here, like this, it's obvious that I still have the applied voltage across each light. Now, this is because that each of the branches is connected directly across the battery. If I move this light over here like this, I have exactly the same circuit. The total voltage still appears across each branch. Now, since the applied voltage is felt across this bulb, I should be able to connect this one like this and still have the applied voltage across it. And you can see that it's starting to look like a parallel circuit. Now, we could add a third branch, a fourth branch, and on and on. Each branch would still have the total applied voltage. Now, this fact is supported by Kirchhoff's voltage law, which states, in effect, that the applied voltage is dropped around each closed loop. All right. A parallel circuit has more than one path for current, and the applied voltage is felt across each branch. Next, let's investigate the current distribution in a parallel circuit. And I'll use another trainer to show this. Making the power connections here. Okay, let's look at the current in a parallel circuit. Notice first that we have 4 milliammeters in the circuit. Also notice that the current leaving the negative terminal of the battery, all of the current must pass through this meter. Then we'll use it to measure the total circuit current. The other meters will measure the current in the individual branches. Now, it'll do that when I close these switches, of course. So let's start by closing this switch. By doing so, I complete a path for current through this first branch. Now, notice the readings on this meter and on this one. They're identical. Well, that shouldn't surprise anyone. We have one branch, a series circuit. So branch current and total current must be the same. Now, watch the total current indication when I close this switch down here. It increased. But why? This is because we added a parallel branch. This second branch is now drawing current from the battery. And if we add this current and this current, we'd find that their sum is equal to total current. Well, let's see what happens when we add this third branch. Closing this switch, watch total current. Total current increased again. In fact, it increased by the same amount as the current through this third branch. Then we must conclude that the total current is equal to the sum of the individual branch currents. In other words, the parallel circuit is a current divider, and the total current is divided among the various branches. Now, there's one other thing that we should have noticed about this circuit. This is the current resistance ratio. For example, the branch with the smallest resistor has the largest current. When we go to a branch with a larger resistance, we find that the current has decreased, so that eventually the branch with the largest resistance has the smallest current. Well, this is only logical since Ohm's law is used to determine current. Remember, the total voltage appears across each branch. Then the current in any one branch must be equal to the applied voltage divided by the resistance of that branch. Now, the total resistance in a parallel circuit is a little less obvious. In this circuit, we observe that each time we added a branch, the total current increased. Then we can say that when we add resistors in parallel, we must be decreasing the total resistance. Well, let's see why this is so. Suppose that these two blocks are carbon resistors. In the lesson on resistors, we learned that the resistance of a particular material is directly proportional to the length. Now, suppose that each block represents 10 ohms of resistance. If I connect the two resistors together, like this, we increase the length. Therefore, we increase the resistance. If we double length, we double resistance. Now, we also learned that the resistance of a material is inversely proportional to the cross-sectional area. For example, if I place these two resistors like this, I've doubled the cross-sectional area. This decreases the resistance by 1/2. We now have only 5 ohms of resistance. Essentially, the same thing happens in a parallel circuit. Each time we add a resistor in parallel, we increase the cross-sectional area of the total resistance. And remember, if cross-sectional area increases, total resistance decreases. Now, if the process of reducing total resistance still bothers you, let's look at it another way. For example, when we open all of these switches, there's no current flow because there's an infinite resistance between the terminals of the battery. When I close one switch, we have current. The added path then reduced resistance from infinity to a specific value. Adding another branch increases current, then total resistance had to decrease. Adding still another branch increases current, total resistance decreases. Now, let's use the ohm meter to prove this. I'll remove this circuit, and what I'm going to do is measure some resistors that have the identical values as the one in our trainer. So let me put this resistor in here. Of course, first we must set the meter up to measure resistance, so I'll put the function switch to ohms, and we'll use a range of times 10. Now, as always, you must zero the meter before using it. So checking the zero, you can see that the meter it's zeroed all right. Now, let's measure this 50 ohm resistor. One connection there, the other connection here. And you can see that we're getting a reading a little bit over 5. We're on the times 10 range, so it's about a 50 ohm resistor. Next, let me connect this 100 ohm resistor in parallel with the 50 ohm. Now check the reading this time. It's about, well, let's call it 33 ohms. Resistance has decreased, but why? Remember, we've increased the cross-sectional area of the total resistance. Now, let's add a 200 ohm resistor in parallel with these two. Watch the reading. It decreases more. Remember, each time we add resistance in parallel, the cross-sectional area of the total resistance increases and actual resistance decreases. In fact, total resistance in a parallel circuit is always less than the smallest branch resistance. In this case, the smallest is 50. And check the reading. It's less than 50. Well, if this is true, then a 1 ohm resistor in parallel with these three should give us a total resistance of less than 1 ohm. So let's try this. Connecting 1 ohm in parallel with these three, you can see that the reading indeed is less than 1 ohm. So we must conclude that the total resistance in a parallel circuit is always less than the smallest branch resistance. And that's current, voltage, and resistance in a parallel circuit. Now, let's go over some important points that we should remember about the parallel circuit. First, remember that the applied voltage is felt across each branch. Also remember that there's more than one path for current in a parallel circuit. Now remember, when we talked about current flow in a parallel circuit, we said that the total current divides among the various branches. If we add more resistors, we decrease total resistance and increase this total current flow. Let's also remember that in a parallel circuit, total resistance is always less than the smallest branch resistance. Now, in the next lesson, we'll talk about power in a parallel circuit. What we've covered here will be very important to our understanding of that subject. We'll also see how a simple device like this extension cord is nothing more than a parallel arrangement. We'll also see how, if it's misused, it can be very dangerous. I'll see you then.